We have a small switch in the program, so the next two talks are switched. And we continue with a talk by Toeno and we'll hear about Coherent manipulation of spins via spin wave mixing.
Yes. Yes. All right. Good morning, and thank you for staying. It's great to have you as an audience. And my name is Toeno van der SAR. I'm from Delft University of Technology in the Netherlands. And now we'll discuss basically a condensed matter topic, but we will use some techniques from quantum optics to drive collective spin excitations in magnets known as spin waves. And we detect those using a spin endowment. And that's basically the sketch that I made here. So here we have a sketch of a typical experiment where we have a diamond tip with a spin. And then we have a magnetic film underneath. And that magnetic film hosts a collective excitation known as a spin wave. And that spin wave generates a microwave magnetic stray field. And we use that to manipulate the NV center spin, the spin endowment. So I will discuss how we use spin wave mixing to manipulate these spins in diamond. Now let me see if I can switch with this thing. Okay. Sorry about that. Okay, just as a background, so I'm from the Quantum Nanoscience department in Delft. This is our physics faculty. And our department has three teams: quantum matter, quantum sensing, and quantum transduction. And because we use a spin to sense things, I'm in the quantum sensing theme. I would like to start by acknowledging the people that actually did the work. And that is my group. Here I will show experiments to which basically all of these people have contributed in one way or the other. There's a few PhD students and postdocs over here. And I would also like to highlight my theory collaborators, with which I have extremely valuable collaborations. And Jaroslav Blanter is here. He's my direct colleague in Delft as well. So today, what are spin waves? So spin waves are wave-like excitations in magnetic materials. In a magnet, all the spins are coupled to each other. So if you jiggle one spin around, it will transmit this jiggling to its neighbor. And so the excitations in magnets are these collective processions of spins known as spin waves. And they form a big research field. And the key drive there is to make spin wave devices that can be used for information processing. You can think of transistor-like devices, but I think the main application is really in these kind of wave-based devices where you use spin wave interference to make, for instance, filters or directional couplers. That's a key drive in the field, but there are other more fundamental and fun topics in spin waves. So you have this bath of coupled spins, and you can think of what are the quantum excitations in that bath. Can we study spin waves in atomically thin magnets? So van der Waals magnets, that's a very hot research topic recently. So today I will, before I go to the topic of the talk, which is coherent manipulation of spins in diamond via spin wave mixing, I will first introduce how we use the spins in diamond to image spin waves. And we do that using a spin in diamond, and these are some of the experiments I will show, and then I will show you how we use spin waves to drive the NV center spin coherently. Okay, I guess I will just stand here. Okay, the sensor of today is the nitrogen vacancy spin in diamond. It's an atomic defect in diamond, on which already a few talks have been given, fortunately, so I don't have to introduce it too much. But it's an atomic defect that has associated with it an electron spin, and we use that electron spin as a magnetic field sensor. Now, if you have a piece of diamond and you have NV centers, so these are called NV centers, in it at the right density, you can detect the NV centers via the photoluminescence. So here we scan a green laser over a diamond and you see individual luminescing spots, basically one NV center per square micron in this case. Now you can use each of these NV centers to measure magnetic fields. And that's nice because these NV centers are point-like defects. So you have point-like sensors of magnetic fields. And then the main challenge to use them for magnetometry is to bring them close to a sample. Now in our lab we developed two ways to do it. So for instance we have this wide field imaging approach where we have a diamond with a thin diamond with a thin layer of implanted NV centers everywhere. 1,000 NV centers per square micron, and so we can image a large area. The challenge here is to get close, because there's always a piece of dust between the diamond and the sample. So when you want to get really close, you use these scanning diamond tips that were also shown by Patrick Malatinsky yesterday. How does it work? So our NV center electron spin has 3 levels, because it's a spin 1, and the Zeeman split as a function of magnetic field. So if you can detect the Zeeman splitting, you know the magnetic field at the site of the NV center. Now, how do you detect this Zeeman splitting? You do that via the spin-dependent photoluminescence. So here, we shine a green laser at the defect and we scan the microwave frequency over the NV center spin transition. And the green laser pumps the spin into the 0 state, and the microwaves pump it into the -1 state, and that gives rise to a dip in the photoluminescence. So that's how you can detect the static field at the site of the NV. Now, another thing you can use this measurement for is to detect the amplitude of the microwave magnetic field. So the stronger the microwave magnetic field, the bigger this dip will be. And this is what I will use to image spin waves in magnets. All right, so how does it work? An introduction to the technique. We place a diamond on top of a magnetic film. So here you see the diamond on top of a magnetic film. So this is an yttrium iron garnet thin film, 200 nanometer thick. We make a strip line on top. The diamond is 2 by 2 millimeter in size. We drive microwaves through this strip line. That will excite a spin wave in the magnetic film. Spectrally, it looks like this. So we have a spin wave dispersion, omega versus k. We apply microwaves of a certain frequency, and that will give us a certain wavelength of the spin wave. And that spin wave will travel downwards away from this microwave strip line. And then we can tune our NV center into resonance with that spin wave frequency. And then the spin wave will start driving NV center spin rotations. And that's basically what you see here. So here you see the NV spin rotation rate as a function of space, away from this strip line that we use to excite the spin wave. And the reason we see a standing wave pattern here is because we have an external magnetic field of the same frequency that's homogeneous. And those spin wave field, traveling wave, interferes with the homogeneous field and gives rise to this spatial standing wave pattern. Okay, so we use this. We use these microwaves of the spin waves to drive the NV centers, and then you can image them. So this is another experiment just to show you what we can do. Here again, I have quite a large area, about 1 millimeter in size, and we have 2 strip lines on the sample. It's again a YIG film. And here we drive the 2 strip lines with the same frequency, and they excite spin waves chirally, because the magnetization here breaks the symmetry. It's pointing to the right in this picture. And what you see here is an image of the microwave magnetic stray field of the spin waves, detected via the spin rotation rate of our spins in diamond. The nice thing is here that we can drive the NV center spins very fast. So that's quantified by this Rabi frequency. So we measure how fast the NV center spins rotate as a function of space. And these spin wave magnetic fields, they travel over millimeters. So you can really drive NV center spins far away from such strip lines. You also see these nice far field interference effects, these funky anisotropic emission patterns because of the spin wave dispersion, etc. And you see there's no spin waves going up in this picture. Now, because the imaging is magnetic, so we detect the magnetic fields of the spin waves, we can actually do stuff that other techniques can't. Namely, we can look through thick metal at spin waves underneath the metal. And that's what you see here. So here we have a gold strip. It's 20 micron in width, and we use it to excite spin waves in the film. You can see it's optically opaque, so you can't look through it. However, if you detect the microwave magnetic field using the NV, you can see the spin waves underneath the strip. And then by analyzing the amplitude of these spin wave fields, you can learn something about the material. So for instance, here you see that the spin wave gets damped relatively fast, and we use that to extract the conductivity of the metal, because that is, the spin wave damping is caused by eddy currents. Now you think, okay, interesting, we have the conductivity of gold, but we already know that, right? But now we can do something more fun, and that is to replace our gold strip by a superconductor. So here is an experiment that we did in the last year. We have a superconducting strip on top of a YIG film, molybdenum rhenium strip with a TC of 8.7 Kelvin. We have a strip line again. We use it to excite a spin wave in the film, and we study the back action of the eddy currents induced in the superconductor by the spin waves on the spin wave spectrum. And here you can already schematically see that the wavelength changes because of this back action. The way we detect it again is with an NV diamond. So we put an NV center diamond on top. So here you see a 50 by 50 micron membrane, 100 by 100 micron membrane of diamond that we placed on top of the magnetic film. Here's the superconducting strip in the center. And then we start imaging the spin waves in this system. And here is what you see above TC. So this is the superconducting strip. In the center, it's a spatial image of 100 by 100 micron. Superconducting strip in the center, but it's not yet superconducting because we're above TC. And you see the spin waves excited on the left. It travels to the right, and the wavelength is unaffected by this metal strip. However, when you cool down through the critical temperature of the superconductor, the spin waves start exciting huge eddy currents in the superconductor. And those eddy currents generate a magnetic field that acts back on the spin waves. So here, the result is that the spin wave dispersion shifts up in frequency, and therefore, if you probe at the same frequency, you will see an increase in the wavelength. So that's what you see here. Almost a doubling of the spin wave length underneath the superconducting strip because of this effect. So it's a way to, the idea behind this experiment is that you can use a superconducting gate to control the phase of a spin wave, and to, for instance, make a fun device. So we can analyze this in more detail, and that's what we do here. So here we see the spin wave length versus temperature as we cool down. For different magnetic fields, you see the spin wave length changes as a function of temperature, and the reason is that it's governed by the kinetic inductance of the superconductor, how strong this back action is. The kinetic inductance, in turn, is governed by the London penetration depth, and that changes as a function of temperature. So here you have a visualization of how the London penetration depth changes as you lower temperature. So what we do is we analyze here the wavelength as a function of temperature. We extract the momentum as a function of temperature for all these different magnetic fields. Then, using a theory, we can convert that to the London penetration depth. We can really see how it depends on temperature. So it becomes small at low temperature, it diverges close to the critical temperature. It's a nice visualization of the London penetration depth. Okay, so final thing before I move to these mixing experiments. So here I show you an image of our superconducting strip where we focus an auxiliary laser onto it. And we think that that laser turns the superconductor normal at the spot of the laser. So now you have a local scattering spot for spin waves. Spin waves are impingent from the left. They scatter on this laser spot. It's what you see here in the magnetic field image. And then if you take a normalized measurement, so without this laser on and with laser on, you get this pattern. So you see you can induce a local scattering spot for the spin waves. And it's nice because if you have such scattering spots, and you can make, for instance, multiple scattering spots, you can make gratings or magnonic crystals or things like that, or mirrors. So that's fun. All right, let me move to the spin wave mixing experiments. No, I have one more result to show. So this is what we do with the NV tip. We go to the nanoscale. So in this case, we have a, sorry, I go too fast. We have a single spin in a diamond tip, and we use it to image a spin wave that's excited by a strip line. Now, what do you expect if you do such a measurement? You expect to excite a long wavelength spin wave according to the spin wave dispersion. So we are exciting this very low K mode, but this is the isofrequency line. So in principle, you can get scattering to all those resonant modes if you can get a momentum kick somewhere. Now, using the distance control that we have with this tip, so we can image the spin waves far away from the sample, then we are only sensitive to long wavelengths. We can also go into contact. Far away, we see this primary spin wave that we excite, but if we do the same measurement in contact, we see all these nanoscale spin waves. And then if you take a Fourier transform of this spatial pattern, you retrieve this characteristic isofrequency contour of the spin wave dispersion. And we believe it's caused by defects. So you excite a wave, there's a defect somewhere, the wave scatters off it. Like you have a wave in water and a rock, for instance. Good, so the final part of the talk is this coherent control via spin wave mixing. So until now, I showed you spin waves that are resonant with our MV center transition, so they can drive the MV center spin directly, and we use it to probe the spin waves. The technique is a little bit limited because we can only detect resonant spin waves, so we try to overcome the limitation by using spin wave mixing. The experimental setup is very similar, so we have a microstrip. We excite 2 spin waves now, of which the frequency difference, or as I will show you later, something else, is resonant. So the mixing product is resonant with our MV center spins. This is this 4 spin wave mixing idea that I alluded to in the beginning. So how does it work? We apply a very strong spin wave pump of a certain frequency that is not resonant with our NV. So then we apply a weak signal, and thereby we stimulate this 4-wave mixing process such that the idler that is produced is resonant with the NV. And we can use now the idler to drive NV center Rabi oscillations. So you can detect spin waves that are detuned from the NV center using this mixing process. And for instance, we have an NV frequency here. We apply a pump here, and that gives rise to an ESR dip. So if we excite a spin wave here, it gets mixed down to the NV frequency. That's how we can detect it here. We can sweep the pump frequency, and then we can detect all these different spin waves that are detuned by about a gigahertz. Okay, so we can do that also coherently. So we use the same process. The NV center frequency is somewhere. We have a pump spin wave somewhere, a signal spin wave detuned from the NV, and then the idler spin wave drives coherent Rabi oscillations of the NV center. So here you drive Rabi oscillations of the NV spins, even though the microwaves that you apply are detuned by almost 600 megahertz. Okay, so we can use this now to probe the spin wave band despite large detunings, and to probe the efficiency of this process. Now, here I show basically the same measurement, except now we tune up the drive power a bit, and then you get higher order mixing processes. So here is a schematic. We have the NV frequency somewhere here, then a pump here, and then the signal frequency here. And you see here now the first order mixing product is resonant with the NV. In this case, the second order mixing product is resonant with the NV. So if we sweep the pump frequency and the signal frequency, you get this whole clump of spin wave of idlers that are driving Rabi oscillations of our NV center. You can detect up to 10 orders. They have a line, so the produced microwaves have a line width that is just limited by the line width of your drive fields, similar to the response of a driven oscillator. Okay, if you vary the pump power, you see all these higher order mixing, well, you see these lines appear and disappear. It's a rich many-body physics of higher order spin wave mixing processes. Okay, finally, so this was, I showed you some results where we used the frequency comp to drive NV center spins. But we can also use the frequency difference between 2 spin waves to drive the NV center. So that is a much lower frequency, and it's depicted here. So here we tuned the NV center to a very low frequency, 35 megahertz. And we drive spin waves within the spin wave band at gigahertz frequency that are detuned by 35 megahertz. And then the difference frequency will drive NV center spin rotations. So this is a way now that you can probe the spin wave band, even though the spin wave band is much above the NV frequency. You apply 2 microwaves, of which the difference frequency is resonant with your NV, like here. So it's a way to probe magnets that have large frequencies. That's a big challenge for NV magnetometry, that those frequencies are hard to address, and so you need to use some kind of frequency conversion like we do here. Now, to sketch a little bit what kind of materials we could probe with this technique, here, this is a measurement done on YIG. You see the dispersion here of spin waves that we can excite reasonably well because they have a low wave factor, low wave number. But it's a very, very small frequency range. We are now working on permalloy, where the spin waves go up to much higher frequency. So these are dipolar spin waves in the 10 gigahertz range. And we can do the same kind of things. It works. So we can, the message here is that we can also potentially probe more exotic magnets, such as van der Waals magnets. And that brings me to my outlook. So that's what we would like to do, to use these kind of mixing processes to probe magnets with an unknown spin wave spectrum, such as these newly discovered van der Waals magnets. For many magnets, the ferromagnetic resonance is unknown, the spin wave spectrum is unknown, and the spin transport parameters, such as the damping or the propagation length, are unknown. So we set out to characterize that. So that brings me to my summary. I showed you how we can magnetically image spin waves underneath metals, such as a superconductor. We can go to the nanoscale using a scanning probe, and then we can probe spin wave bands that are detuned using spin wave mixing. Thank you.